Aha. Okay, let's hope. Yeah, it looks like it's all working. I see myself there, and I'm looking at this little monitor bar, and I see the microphone level meter going up and down. Let's just hope. Okay, now, so this is about the analysis for simple harmonic motion. And if I look like crap, it's because I've been grading your work all day today and yesterday, and it's 5:30. It's sad, and it's so dark out, it seems later. But I've been parked in this chair. It's done wonders for my back, let me tell you. But of course, this is my reward. So anyways, so here, first of all, you gotta have three graphs, three fits. One of them has to do with the part A, and so, I know a few of you will laugh because now I don't remember if it was part A, B, or part 1, 2. But for the first part, we had to just hang weights on and measure the length of the spring. And then we had a test in part 2. There was 2 subparts in the second part, where we had to test various amplitudes and then check the period to see if there was any relationship between the period and the amplitude. And then we were to go on and investigate the period squared, because at the end of the day the formula had a square root symbol, so it was easier to just square both sides and plot t squared in mass. And we'll get to this in a minute. We'll start with the first one. Okay, so you see, you might get a little worried when you see this. You see actual mass and then mass. So actual mass is just the total that was put on, including the hanger, just to get it to an equilibrium position. You don't have to have done it that way. And I don't even remember, this is data from last year or last spring, and I don't even know if it's from a real spring, if it's from a simulation. I mean, it looks like real, and it can't possibly be the same spring that you guys used. Could be. It's hard to imagine. So anyways, what I did is I subtracted so I just call this 0 mass. So I subtracted 50 from each number here. And then that just gave me how much mass was there when the spring was at its equilibrium position. And remember, the criteria was just to hang enough weight on it so we saw that all the coils were open a bit. And so that when we plot this, we would only see the spring constant. We wouldn't see coils that were touching each other and doing nothing. We would see them all come into play. And by the way, another effect that has is that now the spring, the whole spring is doing it, so it makes the effective mass more or less constant. But for us, we're not going to worry about effective mass a whole lot. I have to think about it more to keep it really simple. For us, the big deal was to understand why we made sure the spring was stretched, so all the coils are a little bit open. Okay, so then I used F equals mg for the force, but because we took the mass in grams, I divided the number of grams by 1,000. And I don't know if you guys can see that. Let me, we'll zoom in there for a sec. So there we go. So 9.8, if you like, 9.80 times meters per second squared, that's the acceleration of gravity, g, times the mass, but the mass has to be in grams, so I divided the mass by 1,000. And that's how we get each of these numbers. Now, by the same token, now I haven't added a plus minus mass here because the error in the mass is tiny compared to the error in the length. Because remember, the length is like we're hanging that thing, the weight's on the end of the spring, and then we're using a mirror, and it can be quite a mess. So this was the stretch at the length I measured when it had when I stretched it out enough so that all the coils are open, and I recorded them in centimeters. And really, these things should be only one decimal place. And then I took each one of them, I subtracted the first one, so that's F10 minus F10, F11 minus F10, but at the same time, I divided by 100 to convert centimeters to meters. So that's significant, right? Because the reason it's significant, number one, it's just everything has to be MKS, meters, kilograms, second. What happened is I realized later on when that if I don't make sure and keep everything MKS, it's hard to compare the K we get here to the K we get later on, because this K doesn't have centimeters or meters in it. So I just said the best way to do this is just convert everything to MKS, meters, kilograms, second. So this plus minus is what we estimated when we took the measurement. And in this case, we just, so I got a little fancy here. Let me show you what I did. So we got to zoom out a tad. So since the stretch of two numbers being subtracted from each other, I went to my table here. And you see here's the A minus B. And so that's what I used. And it's fairly straightforward because, well, first of all, little a and little b are 0. This AB part is 0 as well. We don't use the correlation. It's called the autocorrelation matrix. But we're going to stay away from that. We're going to assume the errors, the plus minuses, don't have any relation to each other. So now we have A and B and plus minus A and B, which are the rest length, which is 54.6 in this case, and the error on it. And then we have the actual length and the error on that, and we subtract the two to get the stretch. So I need to calculate the plus minus on it. And notice here there's no sigma A divided by A because it's plus and minus, so it's just a sigma A, which in this case, let's see, what did I call that? Yeah, I call that the plus minus on the length, the particular length, and then this is the plus minus on the rest position. So in this case it's G10 and G10, but now it's G11 and G10. And I suppose we could add some decimal places just so we could see. Excuse me. Now I also here took an average of the data because we need that for the R squared test later on. So I just took the average right away. And then I did my standard fit function And then we got our residual squared. And then the chi-square is just the residual squared divided by the plus minuses squared, the error bars. What else do we have here? So, oh yeah, that's later on. This guy is later on. So then I calculate the data minus the average data squared, which is this SS. And then we make an SS total. So wait a minute, let's view. So let's see. So the chi-squared is just the residual squared divided by the plus minus on the stretch squared, because that's the error bars on the y-axis. And then you take each data point, subtract the average, and that's why the dollar signs are there, and you square that. Now, what else? Oh yeah, error bars. Let's just go back to you have a graph, and you see design, add chart element, error bars. They're already there, but you can, I don't want to mess with what I did. You can pick more error bar options, and then you go here, and stretch is the one, and then I'm specifying a value, and that is, oh, here they are, plus minus the stretch, and both ways, both directions, plus minus the stretch. Okay, and then of course the X error bars I just set to 0, so we don't have them. Okay. So now I've got my fit, the slope, the y-intercept, the sum of the, the sum of the residual squared, the sum of the chi-squared, the sum of the, whatever, I can't remember what SS stands for. Remember, we need it for this right here. And then we got our R squared there. So, let's see. Let's zoom a little bit. View. Okay, so these are just numbers you type in. So we can't see the corresponding. Let's see what we got here. 200. Let's try 150. Okay, great. So we see the sum of the residual squared. Then the sum of the chi-squares. Then the sum of this mess thing here. And then the R value is 1 minus the sum of the residual squared divided by the total. So I think this is the square of the variance, if you want to get fancy. Okay. And then we need to find out what's the plus minus slope. So notice the slope is 0.161. So of course, we've already used the solver to get this. So now I want to have, what's the chi-squared plus 1? So that's 4.054. See, it's 3.054. So I tell it to do that. And so somehow something has happened here. So then we'll go back to this. We're going to copy this. And we're going to, remember, we paste value only. So that's our max slope, I think. It's either the max or the min, because you can't predict which way. When you tell solver to bring sigma chi-squared to a particular value, because it's squared, the slope can go either up or down a little bit. But that's one of the extremes. And then now we go back. And remember, I make sure to paste value there, not paste it. Just don't go paste, because you want to have that number not change. And then we go back to the solver. We tell it to minimize. And we say OK. And there's our slope. There's our extreme. There's our plus minus. See, it's absolute value of the difference between the two. And it's pretty small, obviously. We did a pretty good job. Let's add some numbers, some digits. Now, in this case, the slope is just 1 over that. So that was pretty easy. And now, we have it in newtons per meter, so we have to change that. Great. And now this is in newtons per meter also. Now, how did we get this? Well, since we're just going 1 over a number, then if I have A has no error, it's just I'm assigning the number 1 to be A. The plus minus on 1, since it's a constant, is equal to 0. So now B is the slope, right? 1 over the slope. And then the plus minus slope is the sigma B. So then they end up with plus minus K equals K times the square root of that. And remember, once again, I got it from here. And so then, there it is. So it's the value of K, L20, times the plus minus slope divided by the slope. That gets me to plus minus, and then just to get the relative error, I divided the slope by that much, and then multiply by 100. And this is not like for a accepted value. This is just basically I got a value of K, and the plus minus is about 2.4%. So basically I'm pretty happy. And I also noticed that my R squared value is very close to 1. So I'm also very happy. So this is already almost 20 minutes. So I'm going to stop this one and make new ones for the rest going on, so the videos don't get too long. So stay tuned.